Okay, welcome back to Logic. We are doing 7.3, Rules of Replacement number 1 today. It's going to be 2 lecture videos, one on the 5 rules of replacement that we'll be learning and some general points about what the rules of replacement are as opposed to the rules of implication that we learned last week. And then we will walk through some of the practice problems from the book, and that'll be the next video. Okay, so there are 2 kinds of rules that we're going to be using in natural deduction. Last week we used rules of implication, and this week we'll be learning rules of replacement. Now, there are 2 important differences between rules of replacement and rules of inference. First, as the book notes, rules of inference apply to entire premises or lines in an argument, whereas rules of replacement can apply to either entire lines, or you can break into a line and use rules of replacement to replace parts of lines or parts of entire complex well-formed formulae according to the rules that are given, so that you can't do this just in any way you want, but there are patterns that you can follow, and if you follow them correctly, you can, preserving logical equivalence, replace certain parts of a line for another part of a line. So, for example, modus ponens is one of our simple rules of inference, and here's an example of an incorrect use of modus ponens where the first premise is a conditional that has as its antecedent a complex well-formed formula inside brackets. The antecedent is itself a conditional, and that conditional itself has a disjunction, either A or B, as its antecedent. And this incorrect use of modus ponens here is trying to, if I can find where I just moved from, there we go. This incorrect use of modus ponens is trying to break into line number 1 and infer C from number 2, A disjunction B, and then tack on the arrow D onto the end using modus ponens. And this is not the way modus ponens works. You can't just break into the middle of a complex, well-formed formula in that way using the rule. You can, though, as we've been doing, you can use it to apply to entire lines. So here, this is a use of MP or modus ponens that uses the entire conditional on line 1, and then the antecedent of that conditional, just P, on line 2, and then correctly concludes Q. So, by contrast, rules of replacement, and we'll explain why this is in a second. Rules of replacement, you can break into parts of complex well-formed formula or parts of a line. So here we have the double negation rule, which we'll talk about in a second, but it's pretty simple. The double negation rule says that if you have P, then that is logically equivalent to and replaceable with not P. Here's a correct use of the double negation rule. On line 1, we have that same long conditional, and then line 2 is the same. And here we have just gone directly into those first brackets, and without unlocking, as we've been doing, without unlocking A first, we just were able to use the double negation rule to tack 2 negations onto the A on the left-hand side of that disjunction, even though it's within brackets and not yet unlocked. So only rules of replacement let us do that. Why is this? What's the difference here? Why can rules of replacement, but not rules of inference, be used to break into complex well-formed formula in this way? And the answer is that rules of replacement state logical equivalencies, whereas rules of implication state entire argument forms. So our rules of implication had structures like this. Tells you what you can infer from what, or what validly follows from what. And as we'll see in a second, our rules of replacement have this 4-dot symbol instead of the line-by-line inferential structure. It just has a well-formed formula on one side of the 4 dots and then another one on the right-hand side. Whenever you see the 4 dots, that means is logically equivalent to. So we learned earlier when we were doing truth tables, we saw that well-formed formula with exactly the same truth tables are logically equivalent. We could prove whether or not 2 or more statements were logically equivalent by seeing whether they had the same truth tables. We can now see an application of that. The reason why that matters is that logical equivalence is stronger than just implication. Logical equivalence means literally the propositions are true in all the same possible worlds, or all the same possibilities, their components are true or false. And this is what allows us to use these rules to swap out parts of well-formed formula without having to unlock them first. We're just restating the same proposition using rules that tell us what that proposition is equivalent to. The second difference is that rules of implication are, this is related, one-way rules, whereas rules of replacement are what we can call two-way rules. So here's our modus ponens. Modus ponens is one way in the sense that if A then B on a line, and then if you have A on the next line, then you can infer B. But you can't do the reverse. So modus ponens only lets you make an inference like this one way. If you're given B on a line, you can't conclude, therefore, if A then B, and therefore A. If you just think about substitute in A's and B's for it's raining and the ground is wet, you'll see why that is. By contrast, rules of replacement, like the double negation rule, the 4 dots, because it means is logically equivalent to, these are two-way rules. So when you apply them, for example, P 4 dot double negation P is just the very same rule as double negation P 4 dot P. So a correct application of that rule would take you from a line with A to a conclusion not A. That's equivalent, and you'll justify it using double negation. You could, though, if you're given not A, you could use the very same rule, because it's a two-way rule, and conclude from it A. So you're able to reverse the inference in this way because we're dealing with logical equivalence and not implication. Another way to put it is that logical equivalence is what's sometimes called a symmetric relation, whereas entailment is a non-symmetric relation. Okay, so those are some important details about what rules of replacement are, why they're different and separated from rules of implication. Now we're just going to walk through the ones that we're learning in this chapter, and most of them, again, are relatively straightforward. In a few cases, I'll sort of explain the intuitiveness of it, and in a couple of cases, it's sort of just a here's the rule, and it's not particularly helpful to give concrete examples. So our first rule we have seen before, so I won't go through it in pretty much any detail, but it's nice and handy that you guys have already learned De Morgan's rule, because now we are going to be able to use it when we're doing natural deduction. It is a rule of replacement, so we know that if we have negation, open bracket, conjunction P and Q, close bracket, that's logically equivalent to, and therefore replaceable with, in an argument, not P, disjunction, not Q. And likewise, this is the second part of the rule, so it's a two-part rule. If you have the negation of disjunction, P disjunction Q, that is logically equivalent to not P, conjunction, not Q. So remember, you distribute the negation or the tilde, and you flip the disjunction to a conjunction, or vice versa. The brackets here, strictly speaking, aren't necessary on the right-hand side. And again, it's a two-way rule, so in either direction. I think that when we were doing class in person, somebody asked to write out each of them, and I wrote out all four. Strictly speaking, because they're equivalent, I don't have to write out the second version of each of these because we've got the dot rule here. Here's our second rule of replacement, commutativity. We'll abbreviate it COMM. Commutativity tells us, this one is pretty intuitive, that if you have a disjunction, such as either P or Q, you can swap that out for either Q or P. So this is why I said in class, somebody asked this question earlier on before the break, does the order matter? And the order matters for conditionals. The order does not matter, as we'll see later, for biconditionals. The order also does not matter for disjunction and for conjunction. And that idea that the ordering of the statements doesn't matter if you say it's either raining or it's not, that's logically equivalent to it's either not raining or it is. You're just swapping the grammatical order of those the parts of that sentence. And so those two sentences express the very same proposition, and that's what allows us to swap those out via commutativity. Likewise with conjunction, Ali is both a dog and has long ears is logically equivalent to, doesn't just entail, but just is the very same thing as Ali has long ears and is a dog. You've just swapped the order of the predicates. Our third rule, associativity. This one is a little more complicated, but associativity tells you that if you have P, disjunction, and then in brackets Q or R, you can, without adding or subtracting anything from the meaning of the statement logically, you can conclude from that or just replace it with the logically equivalent open bracket, P disjunction Q, close bracket, disjunction R. In other words, if you have a line of 3 disjunctions and you need to disambiguate, this way of disambiguating is logically equivalent to this way of disambiguating. If we were to do the truth tables for this, you would see, we're not going to walk through them. The same thing goes for conjunction, the exact same structure of the rule. Oops, I've got the wrong letter here. Let me rewrite that real quick. That should be a Q. If you have on a line P and Q and R, this way of disambiguating that long conjunction is logically equivalent to this way of disambiguating it. And that's what associativity tells us. The next rule is distribution. This is perhaps the trickiest one, the least intuitive of this set. But once you see the underlying rationale, it becomes a little more intuitive. So distribution says that if you have a conjunction which on the right-hand side has as one of its disjuncts a disjunction, as one of its conjuncts a disjunction, then that is logically equivalent to the distribution of the left-hand side of the conjunction in this way. So here we have P dot open brackets Q or R close brackets. That's logically equivalent to P and Q or P and R. So if you let P be Ollie is a dog, if you let Q be Ollie is an animal, and you let R be Ollie has ears. You can see that Ollie is a dog, and either Ollie is an animal or Ollie has ears. That's just the same thing as saying either Ollie is a dog and Ollie is an animal, or Ollie is a dog and Ollie has ears. So distribution is what tells us those two are logically equivalent. For P disjunction Q and R, the same thing holds. You can distribute the P and have as a result P disjunction Q and P disjunction R. So, for example, in English, if you had either Ollie is a dog or Ollie is an animal and Ollie has ears, that's just the same thing as saying it is both the case that either Ollie is a dog or Ollie is an animal, and either Ollie is a dog or Ollie has ears. So distribution, it takes a little bit of brute memorization. Try just rewriting it out a few times. Swap out, use P's and Q's to swap it out for English to help you sort of intuitively think through it. And once you've done that, you'll either have just kind of brutally memorized it, or it'll become clearer why it's intuitive. But that's a rule we can use for replacement. Our last rule is the simplest and probably the most intuitive. Double negation. If you have P, that's logically equivalent to not P, or tilde P, and vice versa. So this is like, in English, the double negation is equivalent to just the positive assertion of that statement. Negations stacked on top of each other cancel one another out. And do note that one thing that this means, though, is that if you have an odd number of negations, you are going to end up with the equivalent of that being a negation, a simple negation. So tilde P is logically equivalent to tilde P. Only these two negations cancel one another out, and you've got one negation remaining. On the other hand, if you have four negations, which God forbid, but that does happen sometimes, you will be able to use double negation rule to conclude not P, and then you'll be able to use it again to conclude P. So 4 tildes is equivalent to just P, but you'll have to use the rule twice. Okay, so those are our rules, and we'll walk through some practice problems next.